Hi, this is Dr. S and this is video 13 in my series on reaction rates for Year 13 A-Level Chemistry. In this video we'll look further at the idea that temperature can affect the rate of reaction. And if you remember from Year 12, the Boltzmann distribution can help us show this idea. So if you remember the Boltzmann distribution, we show the molecular distribution of energies, such as this, and we have an activation energy somewhere. And we said that if we increase the temperature, that will change the position of the curve. So it might make it look more like this. And you would see that these extra molecules here are the ones that would be able to react with the added temperature, with the added energy. In Year 13, we introduced the idea of something called the Arrhenius equation. And we can actually do some calculations to quantify the effect of temperature on rate. So let's look at what the Arrhenius equation looks like. So the Arrhenius equation is K equals AE to the minus EA over RT. So that's a power. Now let's go through and make sure we're happy with what all these terms actually are. So K, as we've seen several times, is the rate constant. And you know by now that the K can have different units, so we'll just leave that as a statement here. We can have differing units. On this side, we should recognise activation energy. And normally that has units of kilojoules per mole. I'll come back to that. We should also recognise temperature. And R we've seen before, which is the gas constant. So let's concentrate on the units on this side. We'll start with the gas constant, because this has given units, which is joules per Kelvin per mole. So that gives us an idea about what units we need to use for temperature and activation energy. For temperature, I'm going to need to use Kelvin. And for activation energy, I just said that we normally use kilojoules per mole, but here the gas constant is in joules per mole, or joules per Kelvin per mole. So to make sure they match, we're going to use joules per mole for activation energy. Now what you should see here is that now this entire term here, the minus EA over RT, has no unit. Because on the top I have joules per mole. On the bottom I have joules per mole, so they cancel out. And on the bottom I also have Kelvin and Kelvin to the minus 1. So all the units cancel out to leave this unitless. Okay, what else have we got? We have E. Mathematicians will recognise this. This is the exponential. So this is a number, just like pi. And there should be a button on your calculator that says E on it. The actual number is approximately 2.718. And it has no units because it's just a number. Right, so the other one we've not explained yet is A. Now this has a few different names you might meet. You might see it as the Arrhenius constant. You might see it as the pre-exponential factor, in that it comes just before the exponential. Or you might see it called the frequency factor. Now if you think about what the Arrhenius equation is actually showing you, it's thinking about the things that might affect the rate of reaction to come up with an overall rate constant. Activation energy. If that's high, we'll have a low rate. Temperature. If that's high, we'll have a high rate. Something else that affects the rate of reaction is how often molecules bump into each other. Now that's really hard to quantify. So that's what we brought this in for. The frequency factor is essentially a measure of how many times particles bump into each other. So the last thing to look at is what are the units of the frequency factor or the pre-exponential factor. Well, because all this has no units and this has no units, K and A must have the same units. Now K can have differing units, so that means A can have differing units. So if K is seconds to the minus 1, A will be seconds to the minus 1. If K is dm3 mole to the minus 1, s to the minus 1, A will be the same. So A will always be the same units as K. Okay, in my next video we'll use this equation and we'll perform some calculations on it to determine a rate constant from known factors. I'll see you then.